Good morning. Today in the lecture of magnetic effect of current, lecture 6, I am going to cover the following points. Ampere Circuital Law, magnetic field due to infinitely long current carrying current wire, solenoid and toroid. Now Ampere Circuital Law. Now, according to Ampere Circuital Law, the line integral of magnetic field around any closed path or circle in vacuum is equal to mu naught times the total current I threading the closed path. Threading means the current passing through the wire. Mathematically, we write it integral B dot dl is equal to mu naught I. So this is the Ampere Circuital Law. Now proof of this law. This figure is same as this. Here in place of the current carrying wire, dot is shown. That is, the current is coming out from the piece of the paper, and here the current is anti-clockwise, so again it is shown the current is anti-clockwise. The line integral, that is B dot dl. Now it is a dot product. Dot product means A dot B is equal to AB cos theta. Theta is the angle between A and B. So here the two vectors B and dl, the angle between them. Here at any point of this loop, if we see that magnetic field and dl at all the points, if we take this point, then magnetic field will be in this direction, and the length of the wire also, the current element is also in the same direction. How it is? Using the right hand thumb rule. So magnetic field and dl, the angle between magnetic field and dl is 0 degree. So this is reduced to B dl cos 0. Cos 0 is 1. So this is B dl. Now when you integrate, since magnetic field magnitude of the magnetic field is constant, so take it out from the integral sign. B line integral dl. Line integral means the total length of the circumference, because it is a circular loop, so the circumference is 2 pi r. Now in place of B, mu naught I upon 2 pi r. How? Just recall the lecture 1 where we have calculated the magnetic field due to infinitely long current carrying conductor at its center, at any point. At any point means here the point is at a distance r from it, and this is the wire, this is the current carrying long wire, and at any point which is at a distance r. So that expression we have calculated mu naught I upon 2 pi r. We can use this relation here in place of B. Simplifying it, we will get mu naught I. So line integral B dot dl will give you B is equal to mu naught I. This is Ampere Circuital Law and very important law. Now let us again calculate magnetic field due infinite long current carrying wire, which we calculated in lecture 1 using Biot-Savart law. Here we will use it to find Ampere Circuital Law. So in vice versa, we can say that we are proving the Ampere Circuital Law using this relation by calculating from Biot-Savart law, and now we are proving this result using Ampere Circuital Law. So again, consider a current carrying straight wire in which I current is flowing as shown in the figure. Let us consider a circular imaginary path. Circular imaginary path is the Amperian circular loop. Just like in the electrostatic chapter, we consider the Gaussian surface. Here we are considering the loop which is called the Amperian circular loop or the circular imaginary path centered on the wire whose plane is perpendicular to the wire. Now according to the Ampere law, B dot dl is equal to line integral B dl. B dl again because angle between B and dl is 0 degrees, so cos 0 is 1, so we can write B dl. B taken out, dl, B length is 2b 2 pi r, and also according to Ampere law this is equal to mu naught I, so we can equate both these expression and then we can get B is equal to mu naught I upon 2 pi r. Now solenoid. Solenoid word is quite familiar to all of you. You have studied about the solenoid in class 10th also. Solenoid is a tightly and closely wound helical coil made of a long insulated wire. Its length is very large as compared to its diameter. When current flows in a solenoid, magnetic field develops around it. Just like the basic concept of the magnetic field, magnetic effect of the currents, whenever there is a current flowing in a conductor, magnetic field develops around it. Since solenoid is also a closely helical coil, so magnetic field develops around the solenoid. Now this magnetic field resembles to that of a bar magnet. Now let us understand the magnetic field due to a solenoid. Now at these points, now these are the coil which is wounding in a helical shape. Now at these points, if you see, because from the right hand thumb rule you know that the magnetic field lines will be circular at all these points. So at this point, I have enlarged the figure, so just look at this point. Because of this circle, the magnetic field is in the upward direction, and because of this circle, the magnetic field is in the downward direction. To at this point, just adjacent to this point, one is outcoming from the paper and one is going into the paper. Both are in opposite direction. So at this point, the magnetic field will cancel the effect of each other, while at this point it is both are in the same direction. So we can say inside the solenoid all the magnetic fields they add up, while outside the magnetic field they cancels out each other. At all the points the magnetic field is coming out, and if you look at here, the magnetic field is in the downward direction, which is shown by the cross. Again at the point, two circles at the adjacent points of these two circles, magnetic field is in this direction. Here the magnetic field is in this direction, so they will cancel out. Again look in this direction, and here it is in this direction. So at this point both are in opposite direction, so they cancels out each other. Inside the solenoid the magnetic field is in the same direction, so they add up, and the total or the magnetic strength of the magnetic field is maximum inside the solenoid. Now which end of the coil will be north, will play as a north, and which end will be as a south? There is a tip. When we look at the end of the coil of the carrying current, if the current is anti-clockwise, the direction, then the end of the coil behaves like north. Now from this north, if you make the arrows here, now this is the anti-clockwise. So anti-clockwise means north, and here in the south, if you go like this, then this is the clockwise direction. So clockwise direction means always south, and anti-clockwise direction means north. This is easy to remember. Now magnetic field of a solenoid. Let n be the number of turns per unit length in a long straight solenoid with current I passing through it. A magnetic field is set up in the solenoid, which is shown and also discussed in the previous slide. The magnetic field is maximum inside the solenoid. So, strength of the magnetic field inside the solenoid is given by B is equal to mu naught N I. The derivation of this formula is not in the CBSE syllabus. It was before last 2 years, but now it has been excluded from the syllabus. So you have to remember only the formula. B is equal to mu naught N I, where N is number of turns per unit length. Now this is the magnetic field inside the solenoid. At the ends of the solenoid, the magnetic field drops just half to it. Means if in any numerical it is asked then what the value of magnetic field at the ends of the solenoid, its value will be half mu naught N I. Not toroid. Toroid is also like a solenoid, but if the open ends of a solenoid are connected to each other, then the shape will be like a ring, and now it is known as the toroid. So toroid is shaped like a solenoid bent into circular shape such as to close itself into a loop-like structure. The toroid is a hollow circular ring, as can be seen in the image below, with large number of turns of enameled wire closely wound with negligible spacing between any two turns. Now from this figure, that is the wire, it is going inside. So you can say that this wire is wounded like this, going inside the paper, and this is at this point it is coming out of the paper. So in this figure, going inside the paper, that are shown by the dot, and inside it they are shown by the dot. That is the cross. Cross means going inside the paper, and this is coming from the paper. So you can say that it is like this, coming out of the paper and going inside the paper. Now the magnetic field due to a toroid can be given in this form. Now magnetic field, if we say at this point, then the magnetic field will be 0 inside any point interior of the toroid, because if we consider any Amperian loop, then no current will pass through it. So at all the points in the interior of the toroid, magnetic field will be 0. Similarly, at all the points exterior of the toroid, these are at any point, these are the it is the place exterior region. So at all these points the magnetic field will be 0. Why it is 0? Because if we draw a Amperian circular loop, then the whole toroid is inside at this point and at this point. At one point the current is coming out, and at other point the current is going inside, which is shown in the previous figure by the dot and the cross. So the total effect of the current will be 0. So in all the turns, the resultant, the total total current will be 0, and as a result, according to Ampere Circuital Law, at all the exterior points the magnetic field will be 0, and inside the magnetic at any point in between the toroid, the magnetic field will be equal to B is equal to mu naught N I upon 2 pi r, or mu naught N I, where capital N total number of turns, R radius of toroid, I current flowing in the toroid, small n number of turns per unit length. So that is all for the today's lecture. Now the chapter 4 is almost covered. Every topic of the topic chapter 4 is covered. These are few questions from the textbook. Try to solve these questions. If you have any doubt, you are free to ask me at any time. Thank you.